you have questions, feel free to speak in your microphone or type in the chat. So we're discussing the Cream worksheets from the AP Review Binder. And we're looking at the last 3 worksheets: derivative inverse functions, then related rates, and then additional algebraic techniques for anti-differentiating. So let's talk about derivative inverse functions first. So the one thing that you need to remember, and it's really just very, very conceptual, is that let's say you have a point on an original function. Let's say this is f of x. Looks like that. And you have a point a comma b. Then you have an inverse. Now the inverse is always going to be a reflection but y equals x. I'm going to probably butcher the drawing of the inverse, but I'm kind of doing my best mirror image of that red curve. But you're going to have a point at b comma a. So they're going to be reflections of each other about y equals x. I didn't do a good job drawing the inverse, but it's okay. So if a comma b is a point on f, then b comma a is a point on the inverse. We know this, right? This is the whole definition of an inverse function. So what this means is that f prime of a, if I evaluate the derivative of the original function at x equals a, that will be the reciprocal of the derivative of the inverse evaluated at x equals b. Remember, b was a y coordinate that went with x equals a on the original. So now we use the input on the inverse, which is b, and we say this. So that's what we say. So let's do maybe a couple of these here. And I'll have you guys try some of the ones below. So let me kind of get us warmed up with number 1. F of x is an increasing function where f of 5 equals 7, f prime 5 equals 13. Find the derivative of the inverse. Evaluate at 7. Okay. I'm not sure why it has to have an increasing function. I don't think that's really relevant, to be honest with you. But what does matter is knowing this. So what I like to do is I like to make just a quick table for f and f inverse. So 5 comma 7 is clearly a point on the original. Therefore, 7 comma 5 must be a point on the inverse. Okay. Well, what this means is that f prime of 5 must be 1 over the derivative of the inverse. So you do the inverse notation with the derivative symbol, evaluate at 7. F prime 5 knows 13. 13 equals 1 over derivative inverse, evaluate at 7. So that derivative, oops, forgot the little derivative symbol, is going to be 1 out of 13. And there you go, 1/13. That's all. Let's try this again for number 2. Actually, you know, let me do number 3. I'll have you guys try 2 on your own because 2 is very similar to 1. Let me do number 3. A little weird with the table there. Okay, for number 3. Use the table below to find the derivative inverse evaluated at 1. Okay. So kind of like to do this first just so I don't get too lost. So 1 is the input for the inverse. That means that 1's the output for the original. So you start with that. Again, 1's the input for the inverse, so 1's the output for the original. Well, 1's the output for the original, the input's 3. Therefore, 1 comma 3 is on the inverse. So 3 comma 1 is on the original, as the table indicates. 1 comma 3 is a point on the inverse. Therefore, g prime of 3 must equal 1 over the derivative inverse evaluated at 1. Because remember, 1's the input for the inverse, 3 is the input for the original. Do I know g prime 3? Absolutely. -3/4. And it's reciprocal of the derivative inverse evaluated at 1. So that's going to be -4/3. So yeah, it's not that hard once you get the hang of it. And you're going to see probably a couple of these, and they'll make it kind of like this. Now, notice how some things were irrelevant. That was not relevant. That was not relevant. The first two rows we didn't even have to use at all. But it kind of trick you by putting the 1 there and a 1 here. Right? So be careful about that. They do try to trick you a little bit. We got looks like a new person joining us. Welcome, John. Okay. So John, just so you know, we're going over the CREAM worksheets from the AP Review Binder. We're focusing specifically on the last 3 worksheets: derivative inverse functions, related rates, and additional algebraic techniques for anti-differentiating. So those are the 3 we're going to talk about. And I just did a couple of problems, number 1 and 3. And don't worry, I record this, John. So if you didn't, if you want to, watch it later, you can. But we did with number 1 and 3. And the key idea for derivative inverses, again, is to make a table. So if I just redo number 1 again, just since John just joined us, f of 5 equals 7. Let's make a table for f and its inverse. So 5 comma 7 is a point on the original. Therefore, 7 comma 5 is a point on the inverse. And this is the key concept. F prime 5 equals 1 over the derivative inverse evaluated at 7. Remember, using the inputs for the original and the inverse to set up this reciprocal relationship. So evaluate the derivative of f at 5, evaluate the derivative of the inverse at 7, and those are reciprocals of each other. And because f prime 5 is 13, then therefore the derivative inverse valued at 7 is 1 out of 13. And that's what's meant by this A and B notation here, just so we know. Okay, so I'm gonna have you guys try 2 and 4 as well. And with that, try 5. So let's just do the rest of this worksheet. I'll give you guys maybe about 5 or 6 minutes, and then we'll talk about the answers. I'll pause the recording because I just don't think it's worthwhile to have 5 or 6 minutes of memory taken up, a long silence. So I'll pause the recording. I'll restart it when we go over 2, 4, 5. And by the way, all the answers for these are in Schoology. They're all there. So if you want to check to see if you got these right while others are still working, you totally could do that. Just so you know, for number 4, when you see this notation here, that's from Algebra 2. This tells me that G and F are inverses of each other. By the way, do not try to find the inverse of this. Don't waste your time doing it, because if you do that, y equals x cubed plus x equals y cubed plus y. It's impossible to isolate y here. Do not do that. Use this relationship between the derivative of the original and the derivative of the inverse, that they're reciprocals of each other. That's what you got to do. But of course, we have to also realize that G and F are inverses with this, composite function notation. Because whenever you do a composite and it equals the reverse of the composite, so if G of fx equals f of G of x, and the result is just x, that indicates they're inverses of each other. And of course, 5 is another inverse one. So go and try 2, 4, 5. You could feel free to put questions in the chat. If you know the other people here, feel free to FaceTime them or text them. Or if you guys want to just talk to each other while I'm here present, that's fine too. But we'll do 2, 4, 5. We'll give you guys about 5 or 6 minutes, and then we'll go over it. Okay, so let's talk about 2, 4, 5. So I'll direct you to the answer key. And ask questions if you're stuck, or if you still don't quite understand the solution. So for number 2, the answer will be 1/3. So remember, 0 is going to be the input of G, and G is the inverse. And that means that 0 is the output for F. So if 0 is the output for F, you have to solve for X and figure out what X is. Well, hopefully you know your logs. The log of 1 is 0, so that's why it's 1 comma 0. So you have to do that first. So therefore 0, 1 is on the inverse. So F prime 1 equals 1 over the derivative of G. G is already the inverse, so you don't have to do the inverse symbol or notation of 0. So then you can find f prime of x, which we know is 3 over x if you know the derivative logs. And if you plug 1 in, you get 3. Flip it, get 1/3. For 4, g of 2 is easy. Just plug 2 in. You get 10. That's not that hard. So 2 comma 10 is on g. If we call g the original, it doesn't matter which one. We call g the original, f the inverse, or vice versa. I don't care. But 2 comma 10 is on g, then 10 comma 2 is on f. So g prime of 2, which I can find g prime of x, that's easy, that's 3x squared plus 1. Evaluate it at 2, which is going to be 13. Flip it, you get 1/13. Is that right? Yeah. Which is actually interesting as the answer for number 1 also. And for 5, they give some stuff that's irrelevant, so don't feel like you have to use all the information. So again, you want to evaluate the derivative of g at -3. So we'll call g the inverse, right? Because they said so. So again, f g, you see, the same thing's happening here. -3 is the input for the inverse, so it's the output for the original. When -3 is the output for f, the input that goes with it's 2, so therefore -3, 2 is on the inverse. So f prime of 2 equals 1 over g prime of -3. So I'm not going to use this one. That's totally irrelevant. And I'm not going to use that one also. Even though you see a -3 there, you're not going to use f -3 or f prime -3. They put that there to throw you off. When I say they, the College Board. And so f prime 2 is -1/4. Flip it, get -4. Okay. So hopefully we're okay with all that. So let's now move on to related rates. Related rates could be a little intense. So I think what I'll do is I'll do 1 in 4 perhaps, because 4 is kind of intense. And I'll do 1 also to kind of get started, and I'll have you guys try 2 and 3. And 2 and 3 you might need probably, I mean, here's the thing with the AP exam. Yes, you got an average 2 minutes per question for multiple choice non-calc, and I'm not sure if these would be non-calc or calc. Some might take a little longer, and I think it's okay to spend a little bit more than 2 minutes, but it means that you'll have to be faster with some other questions. Hopefully derivative inverses, you're a little faster, or a very typical derivative or integral one, you're fast with that one, because there'll be some gimmies along the way. So don't mull over those. You gotta move fast. So let's look at number 1. Matthew is visiting Gregory at his home on North Street. Fine. And Gregory realizes that Matthew left his wallet and begins to chase him. So Gregory's going south. When Gregory is 3 miles from the 90-degree intersection, so Matthew's going east. Traveling at 40 miles per hour. So Gregory's going 40 miles per hour toward the intersection. Matthew's 4 miles along East Street, traveling from the intersection 25 miles per hour. At the time, how fast is the distance between the 2 men changing? Okay. So I'm going to draw a right triangle like that. I'm going to call this A. Actually, let's call Y, X, and Z. Because Gregory's going on the Y-axis, Matthew's going along the X-axis, and Z is the distance between them. So the first thing you need to do is you need a relationship for all the variables involved. And so what's the relationship? Pythagorean theorem. That's why sometimes people get stuck with this. It's not because of the calculus, it's because they just don't know how to get started. A lot of it's just going to be geometry. You just have to know your geometry principles. That's Pythagorean theorem. So you have to be able to see that. And also I'm going to do something called a snapshot. I'm going to do another diagram. I call this kind of a snapshot because we want the speed at a particular moment, the speed at which the distance between them is changing. At the moment when Matthew is 4 and Gregory is 3, therefore this is 5. Okay, so we know this. Also, the rates are given. So Gregory obviously is traveling 4 miles per hour, and he's actually losing distance, by the way, right? So this is kind of tricky. So because Gregory's distance is y from the intersection, his rate is dy over dt as a derivative, and it's -40. For Matthew, he's gaining distance, so it's going to be a positive rate, and of course it's 25. You call it dx over dt. So you got to do all the stuff to prime the problem, get it ready to go. It's kind of like if you're painting a room, which I've done one time and I'll never do again, because even though it's a lot cheaper than paying a couple grand for someone to do it, it was you know, you got to prime things. You got to put like primer on the wall. You got to like buy the stuff. You got to, you know, put the mat down. Like that's kind of what you're doing. You're doing all that legwork. Once you paint, it's not that hard. Just don't mess up. But you know, that's what you do here. You do 2x times dx dt plus 2y times dy dt. So it's implicit differentiation. This is an application of implicit differentiation because we're taking the derivative of both sides with respect to t, and none of our variables have t in them. So, you know, you got to put that dx dt, dy dt, and a dz dt. So 2z times dz dt. So again, diagram, figure out what you have, the information, come with an equation that relates to everything. That's why it's called related rates, because then you do a derivative, you're relating the rates with this equation, then you substitute and you solve for the rate that you want. So what am I substituting here? Obviously x is 4 and y is 3 and z is 5. So 2 times 4 and dx dt is 25. Y is 3. dy dt negative 40. Be very careful about that. They're not going to tell you, so you have to physically understand the problem. Then z is 5. And then dz dt. And then at this point, it's just, you know, doing arithmetic and algebra. 8 times 25 is 200. 2 times 3 is 6, but minus 240. That's 10. dz dt. We're almost home free. You get negative 4. And because it's negative, that means that the distance is decreasing. So this is dz dt. So dz dt is losing distance or losing length. So they're obviously getting closer together, not further away, because it's a negative rate. Questions about that one? Okay. Just so you know, these notes are in Schoology. Just to point to you where they are. I may have just put under lecture notes. Let me double check. I do. And I think it's 5, 6, if I'm not mistaken. So even though we didn't do this during our sessions 1 or 2 for A and B periods respectively, I did put all the notes. May have under leftover topics as well, but yeah. And you can see that I even kind of spell out the steps here. You know, read the problem carefully. What is changing? What sometimes some things say constant, like a ladder problem. If a sliding ladder is a very classic related rates problem. The ladder doesn't change length, but the distance from the top of the ladder to the ground changes, and the distance from the foot of the ladder to the wall is also changing. So you got to figure all that stuff out. Do 2 diagrams, one labeled letters, one with numerical columns, which I like to call the snapshot moment. Identify what you want to find. Like figure, okay, what do we have to figure out? Come with the equation, relate everything. Then do the derivative, plug in what you know, and solve it. And make sure you state your units. Actually, I should have stated my units was miles per hour. Forgot to do that. And you never, this is a mistake some people make. They want us, because they memorize things, they don't understand. They substitute the snapshot value for differentiating. You know, well, everything's 0 because derivative constant is 0. No, you got to do the derivative first because you're trying to solve for the rates, right? You got to understand what you're trying to do here. And then you substitute after you differentiate. Be very careful about that. It's not that hard once you get the hang of it. And I wonder if I actually have, I may have videos on this too. Hold on a sec. Ooh, I might have it here. I probably should label this a little bit better. I may have done under this week. Well, it's empty. Okay, maybe this week. Okay, yeah, I have them right here. So you can see I have some videos on it. So if you click on week 1, I have the leftover topics from chapter 5. I'll label a little better for you guys. But it's there. if you need to review that stuff, and the filled out notes, all that stuff, worksheets. So it's all there if you want more practice with that topic. Probably show up maybe 2 or 3 times in the AP. Definitely as multiple choice. Maybe it might sneak in as a free response as a part of a problem. You know, they don't fully dedicate a full response for it, but maybe it might be part of a problem. Okay, let me do 4, because that one's kind of a doozy. And then I'll have you guys then try 2, 3. Okay, for 4. So you have a conical container, and it's leaking water, but also water is being pumped in. So there's rate in and rate out, okay? The height of the tank is 60, the top diameter is 20. And we're curious to know what's going on when the water height is 10. And also, we are told that the water level is rising at a particular rate. So we want to know, find the rate at which water is being pumped into the tank, okay? Well, here's where it's a little tricky. Water is being pumped in, water is also leaving. And we also have volume too. So the way you want to think of this, dV over dt, that's the rate at which volume is changing, okay? Volume is changing. Well, what's impacting the volume? The water coming in, the water coming out. So you could probably think of it like this, dV over dt equals the rate in minus the rate out. And they're asking for the rate in. So we actually want to solve for this. Well, I know the rate out is 75. That's a constant. But dV or dt I can actually get by taking the derivative of that. Okay, so you have to kind of understand what's happening here. And so if I draw this diagram again, here's the height, here's the radius. Sorry, there's a radius. And you do have a kind of relationship you could actually establish here. When the radius is 10, the height is 60. So it is actually going to be like similar triangles in a way. Because when the height's 10, we could probably figure out what that radius is also. So we do need to do a snapshot here as well for our particular moment. When the height is 10, what will the radius of that water level be? Well, here's the thing. 10 over 60 equals R over H. It's going to be like similar triangles, right? If you think about it, you have these 2 right triangles. You have these radii that are parallel to each other, so and they share this angle. So all the corresponding angles are the same. So R of H is 1/6. It reduces to 1/6. R of H is 1/6. So H equals 6R. Or say R equals, actually that's fine, because no, we do want to substitute for R. I lied, because we know that the water levels change at 5 inches per minute. That's dH over dt, by the way. So I'm going to do is I'm going to substitute for R. It's getting a little messy. But I'm going to substitute for R here. So V equals 1/3 pi. R is H over 6. Okay, R is H over 6. According to our relationships here. Squared times H. Okay. And let's go ahead and erase the stuff here. Okay. So now we're going to start doing the calculus. V equals, that's 1/3 pi times H cubed, because you have H squared times H over 36. That's 108. So pi over 108. So dV over dt equals pi over 108, that's a constant multiple, times 3h squared times dh over dt. So now remember, the snapshot is when height is 10. Actually, I didn't even solve for what the radius was here, but I know it's going to be a 6. I know it's 10/6 or 5/3, but I don't think it really mattered. But we did have to come up with a relationship of R and H as substitutes. That's where the cone ones are a little tricky, because you don't want it. Otherwise, you have to wind up doing a product rule, and you don't know what dr over dt is. I mean, you could solve for dr over dt, I suppose, but just much easier to replace R right away to make this problem cleaner. Substitute stuff, you know. So let me make some space here for us. Substitute the stuff that we know. dv over dt equals 3 over 108. That reduces to 1 and 36. Hard root that dark background, so pi over 36 times h squared. Remember, h is 10, so times 10 squared. And dh over dt is 5, and it's gaining. It's rising, not going down, not decreasing. So you wind up getting 100 times 5, so you get 500 pi over 36. So I use my calculator. So I get about 40, close to 44. I got like 43.6. But notice we put A as a trap. That's dv over dt. Remember what we said earlier, dv over dt equal rate in minus rate out. What's your rate out? 75. So dv over dt is roughly 44. So 44 equals the rate in minus 75. So you add 75 to it, and you get D119. So the answer is D there. And even you can see there's some hints down below in italics how to actually approach this. So that's related rates. Okay, so I'm gonna have you guys now try 2, 3. I'll give you guys probably about 7 or 8 minutes to do this. We'll talk about it. Then we're going to do the additional algebraic techniques for anti-differentiating. See how that goes. And then if we have a little time at the end, we'll do some multiple choice practice from the packets. So go ahead and try 2, 3. I'll pause the recording just so we don't waste space. Okay, so we're recording. Let me show the solutions for those related rates problems. So right here. Okay, so the answer is D for number 2. They're asking for how fast kilometers per minute is a beam of light moving along the shoreline when it's 1 kilometer from point P. And that does vary the horizontal leg. But the lighthouse and P don't change. So they're trying to solve for the hypotenuse here. You do know that it makes 1 revolution per minute. Well, 1 revolution is 2 pi radians, just so you know. So d theta over dt is 2 pi, just so you know. And we could use tangent to relate this. Tangent is x over 2. Deriv tangent secant squared theta dx dt. And you know, it would help to find the hypotenuse, so we could do the secant, so we can evaluate it and do secant squared. But again, we're trying to solve for the rate for the horizontal leg, not the hypotenuse. Sorry if I said that earlier. And they solve for dx through dt, and you get 5 pi. And then this is a cylinder. The radius and height. The radius does not change. Actually, does it change? Hold on. Oh, it is decreasing. I didn't see that. Okay. It's a tube in shape. So, okay, the height is increasing at that rate. The radius is decreasing. At the time that the radius is 4 inches in length. So you do I mean, you have a snapshot, obviously when R is, rate's 14, R is 4. And you have the rates for both dH and dr. dt trying to solve for the lateral surface area. That's 2 pi RH. They give it to you right there. So did a product rule. I'm not sure how R and H would be related exactly, unlike a cone where you do similar triangles. So you just kind of do product rule and plug in the rates, and you should get C for that one. So questions about those related rates problems? No? Okay. Okay, the last worksheet we're going to go over will be additional algebraic techniques for anti-differentiating. So we are going to run into, this is more of a recent thing. You are going to run into some integrals that just look a little weird, like 1 over x squared plus 6x plus n, where you can't really do a u sub. So what you could do is you can actually do completing the square. In case you guys forgot, what you do is you focus on x squared and 6x and push the 10 off to the side. You take half of the linear coefficient, which is 6, and square it, which is 9. And then you got to put a minus 9 to be balanced. Then you could actually do your factoring, because it's a complete square, put in plus 1. So now you're integrating this. Now we could do a u sub, let u equal x plus 3. So you have 1 over u squared plus 1, and hopefully recognize that's an inverse tan derivative. Hopefully you can recognize that. The derivative inverse tan is 1 over u squared plus 1, so it's the antiderivative of that is inverse tan. And of course, when you do we do this part, du equals du over dx equals 1. I said dx is just du. So it makes a very seamless substitution. You might get something like this that's really weird, where again, a u sub right away won't work. But because you have a single term down below, you have the liberty of actually breaking apart this fraction in this fashion, and then you just do the integral of each term separately. So look for that. Or again, u sub wouldn't quite work as well right away. So you can do long division or synthetic division to rewrite this expression. You might remember synthetic division. If I kind of walk through that process again, you put all the coefficients here, and any term that's skipped over. So you have start with x cubed. There's no x squared, no x terms. So you put 0 as placeholders. Put -2 here because divided by x plus 2. Drop the 1. Multiply, add, multiply, add, multiply, add. So these numbers are from the coefficients of the quotient. So these are equivalent expressions. Then you integrate this. And that's not hard to integrate. You just do each of those separately, and you're fine. You can do long division if you want to get the same results. Sometimes you don't have a choice but to do long division, like the case of example 4. That'd be a little cruel because the u sub again won't work quite as well. Like if you had like x squared plus 2 over x cubed, you could do a u sub because you let u equal x cubed, and then you have 1 over u, and the antiderivative that's ln, natural log. But you could do a long division there, as you see, you get x minus the remainder of 2x over x plus 2, and then you just antiderive that, and then the second fraction, or the fraction 2x over x squared plus 2, does require a u sub, so you do that. And then you have some problems here to try. So let me do a couple of these, and I'll have you guys try some. So let's look at number, let me do ones that are a little more complex. Let me do 3 and 4, and I'll have you guys try maybe 1, 2, and 5. So for number 3, what I'll probably wind up doing is rewrite the integral as 4 times 1 over, and pull out a 3 from here. Like that. So I can pull 4/3 out. Like that. Okay. And that's going to be inverse tan. Times 4/3. And if you were to do this, you would get back to that. Oh, plus c. Sorry, don't forget about the plus c. Okay. So that's that one. Let me do this one up here. I'll do synthetic division because I have just a linear expression dividing by it. But 1, 0, 0, -5. Drop the 1 down, multiply 2 to 1, 2, add it to 4, 4, 8, 3. So I'm getting x squared plus 2x plus 4 plus 3 over x minus 2. And that's what I'm integrating. So you're using the algebraic technique to rewrite the integrand. Then, of course, I get x cubed over 3, just plus x squared, so I get 2x over 2, the 2's cancel, plus 4x, plus 3 times natural log of x minus 2 plus c. And if you were to do a derivative of that and clean it up, you would get back to number 4. And again, the answer that you have, unfortunately, I was able to find all these. This is Ms. Blanford's handwriting. Yeah, you see I have that right there. So anyway, let me have you guys try. One, 2, 5. Go and try 1, 2, 5. We'll check in about maybe 6 to 8 minutes, roughly. And then I'll kind of point you to some problems in the multiple choice packets, and then we'll start wrapping up our session for today. So 1, 2, 5. I'll pause the recording. Okay, so here's the solution key for number 1. So again, you just want to divide each of the terms by x squared. So you get that x cubed minus 3 plus 7x negative 2. And you have to derive that. For number 2, it's square, so that's a little tricky. So you could expand it and then work it out. So that's not too much spoiling. And then for 5 is very similar to number 3. You this case you can score like the example did on the previous page, or 2 pages ago in this worksheet. So you do complete a square, take half negative 10 squared, you get 25. But then, of course, you have to subtract 25 on the other end. 26 minus 25 is 1. Or you can get a little clever and rewrite 26 as 25 plus 1, so you can have a perfect square trinomial, factor it, inverse tan, there you go. There's a couple more on the other pages if you want to try that. We have about 15 more minutes, but I do actually have to, because I'm actually can't tell I'm home right now, so do need to get to campus. And we have office hours. I don't know if it'll show up for office hours, but you know, it's just a process getting on campus these days. But let me kind of just direct you to some multiple choice problems you could try. So if you look at some a little more recent, like maybe the 2008 multiple choice, well, not that recent, but a little more recent than the other ones. Actually, I don't care for the answers. Hold on. Multiple choice, non-calc. Yeah, so that's a limit problem. That's not that hard. Integrals. We have derivative. That's pretty straightforward. No limit problem there. Not sure we'll see related rates in here, maybe. Velocity, no derivative. FTC style problem. Riemann sums. Graphing the derivative from the original graph, vice versa. More derivatives, more derivatives. That's actually going to be a chain rule type of derivative. Table with understanding points of inflection, first derivative test. U sub, that's a good U sub problem. Implicit differentiation. You can see there's a FTC style problem with that one there. That's a good derivative problem. Horizontal deal with limits as x approaches infinity, points of inflection. Something with vertical motion. Look at derivatives, differential equations with law of exponential change. Another differential equation there. Linear approximation, which shouldn't be too hard. Limits, continuity, slope fields, and of course, finally have an inverse one here at the end. So I would do that. Try 2008. I'll talk to Sydney and make sure she goes over that with you guys and talks about it and records a session as well. And I think we'll go ahead and end it just a tad early for today because I do have to head to campus. But I will be present for this session again on Friday. I am going to be available on Sunday as well from 1 to 3. I'll send an invite for that, email everyone, and I'll share this link as well. And you guys have the playlist. So I'm going to go and stop the recording.